Welcome to Spring LIB.
So in the first part, we need to find the threshold wavelength, and in the second part, we need to find the work function for this surface. And in order to do that, so in order to find the threshold wavelength, we can use this equation where threshold wavelength is equal to speed of light over threshold frequency. Now let's call this equation 1. So from here we know that if we find the threshold frequency, we can find the threshold wavelength. So in order to find the frequency, the threshold frequency, we will use the following equation, the equation for photoelectric effects. So maximum kinetic energy is given by total energy, and here the energy is at the threshold frequency minus what function. So we can apply another condition here. Since we are using threshold frequency, we know that at threshold frequency maximum kinetic energy is zero, because there may be emission of photoelectrons, but there is no kinetic energy associated with the emitted photoelectrons. So thus this means that phi is equal to the threshold energy. So we need to find phi in order to find the threshold frequency. Now let's call this equation 2. We will need to use this later. Now to find phi, the work function, we will use the following equation. This is also equation for photoelectric effect, but here we have the kinetic energy expressed in terms of the stopping potential. And this is equal to the energy of light, or energy of photons, minus work function. So the first equation for photoelectric effect, we solved it for the threshold case, and the second equation is for any general case. So this means that phi is equal to HF times EV naught, where V naught is the stopping potential. And we also know that from this equation, we know that frequency is c over lambda, and this is the same equation that we used here and applied it for the threshold case. So uh, now we have all the information we need to solve this equation. So we know Planck constant 6.626 times 10 to the power minus 34 joules second. Speed of light is 3 times 10 to the power 8 meter per second. Lambda is given to be 254 nanometers. So 254 times 10 to the power minus 9 meters. And V naught is the stopping potential, and that's given to be 0.181 volts. And one last thing, charge of the electron, and that is 9 point oops, that is yes 9. Okay, so we don't need that, because uh, E times, we will have this after multiplying it with the charge of electron, we will have it in units of volts, but we can just keep E as it is, and then we will have this EV naught expressed in terms of electron volt. And we know that 1 electron volt is 1.602 times 10 to the power minus 19 joules. So we need to convert this factor with this in order to have this factor EV naught expressed in terms of joules, because we are using H, the Planck constant, in units of joules. So in order for our units to be consistent, uh, we need to solve this. We need to have the EV naught, the stopping potential energy in terms of joules. So now substituting all these values, you should get phi to be 7.53 times 10 to the power minus 19 joules. So now we have the work function of the surface. Let's uh, convert this into units of electron volts. We already have the conversion, so we just need to divide this factor uh, over here. So that will give us, so we need to divide 7.53 by the value of by the conversion factor. So this is in joules, and then we have, this is joules per electron volt, and that should give us phi in units of electron volt, and that is equal to 4.7 electron volts. As you can see, this is again in terms of electron volts. So yeah, that's the reason we didn't substitute, or we didn't plug the charge of E over here and multiply that with the stopping potential, because we need this unit to be expressed in terms of electron volt, so that we can convert this electron volt into joules and solve the equation. So now we have the stopping potential that is required in part B. So that's the answer to part B. And after having phi, we can find the threshold frequency by using equation 2. So again, the value of H that you'll be using here should be in units of electron volts. So instead of converting H into electron volts, you already have phi in units of joules. Let's call this equation 3. So we will use this value of phi and substitute this along with this value of H in equation 2. So that will give us the threshold frequency. So that is equal to phi expressed in terms of joules, and then H expressed in terms of joules as well, joules and seconds, in order for units to be consistent, and this gives frequency to be 1.14 times 10 to the power 15 hertz. You can choose to use this value of phi that is expressed in terms of electron volt, but make sure you use the value of H in terms of electron volt as well, or convert this unit of H, convert this value of H into electron volts by using the conversion. So either way, you should get the same result. So that's the threshold frequency, and then we can plug this back into equation 1 and find the threshold wavelength. So that will give us the wavelength to be equal to 2.64 times 10 to the power minus 7 meter, and this is equal to 264 nanometer. So that's the answer to the first part, where we need to find the threshold wavelength. This is the answer to the second part. Now, by checking table 38.1, where, so in part B, we have to compare our calculated value of work function with the one that's given in table 38.1. So we compare that by taking the value from part B, and we see that the calculated value of the work function agrees with the copper work function value in the table. So this means our metal here is copper.